Okay, all right. So, hi everyone. Thank you very much for coming tonight or today, this morning, depending on where you are. Um, I'll be sharing my screen. Can you see everything fine? Good. So, yeah, just a little bit about myself. I'm a what's going on? Yeah, um, assistant research professor in Cambridge at the Leverhulme Center for the Future of Intelligence. I've been here for a couple of years working on AI evaluation for the most part. Um, my background is in statistics and machine learning. Well, even before then, I was a physicist. But I chose to pivot towards working more on AI evaluation because I feel like it's a really important and topical problem to kind of address. So today I'm going to talk about this paper, which I co-authored over, I think it was 6 months ago, or probably even more at this point, which is which is called PredictaBoard, benchmarking LLM score predictability. And this is kind of part of um, a suite of work which I'm doing, but other people in my team are also doing, where we try and basically build, like develop new paradigms for AI evaluation. And I'll jump right in, starting from some motivation. And the whole motivation of this paper is the fact that if you basically let's assume you have a benchmark, right? Let's assume you have a benchmark and you get a score out of it. Uh, so we felt like by looking at it, we felt like this is not really super informative. Wait, I see someone's moving their pointer. That's what's going on. Okay. All right, that's weird. Um, anyway. Um, interesting.
Maybe this can be disabled in the same
Yeah, I'm
way.
trying to find that. How can I disable that? Um, what that? No, I have no clue.
I believe that it's something to do with the share button on Zoom. Um,
Is it?
so it's a little bit difficult because I think if
Yeah.
you do advanced sharing options, perhaps.
Wait, I
I
can't
think,
read.
is it gone now?
Oh, advanced sharing options. Okay, I see. Okay, yeah, I don't see it anymore. Okay,
I think
great.
I may have been able to disable it. Thank
Okay,
you,
great. Thank you
Lorenzo.
so
Sorry
much.
for that.
No, that's okay. Don't worry. Okay, so just getting back into it. Wait, no, I see it again. What? Okay.
Oh my gosh.
Okay, never
So
mind. I'll
sorry.
just go ahead. That's
Okay.
fine. Don't worry. Right. So what's the point? Let's imagine you have a benchmark. Well, of course, what you usually get out of a benchmark is a sort of average score. But what we felt is that you don't really get too much information, or at least like as much information as you could from just looking at this score. And I guess as kind of a motivation example, I usually consider this kind of example of a self-driving vehicle, for instance, or let's say an AI system which helps with a car with car driving. And let's assume for simplicity that the set of conditions which you may have on a road is described by a two-dimensional space, right? So one dimension is the windiness of the road, so like how many curves you have, while the other dimension is the fogginess, so how foggy it is. So, well, given this set of conditions, you may imagine several systems. So here on the right, I've described 6 different systems from A to F. And these systems may have different patterns of performance. So let's say system A has a green box, which represents perfect performance for all cases where the path convolution or windingness is very low, independently of the fogginess of the road. And as you can see, system B has kind of the opposite kind of behavior where the windingness of the road doesn't matter, but the fogginess has quite a significant impact. And you can imagine some other cases where the windiness and the fogginess of the road somehow interact. So the system has a high performance if some kind of combination of them is low enough. But you can also imagine cases potentially where the system has a performance which is basically unpredictable from the fogginess and windingness of the road. And what's interesting is that in all of these cases, let's say in this kind of toy example, you may have kind of the same average or the same accuracy on the overall set of examples which you may encounter, let's say, in the normal operation of a self-driving car, right? So what's the point here? Like, what point am I trying to make? What I'm trying to make here is that basically system A and B are actually much more useful in the real world, because if you are actually able to say, look, I will give you this self-driving kind of this autopilot for your car, and you know precisely when you can trust it or not, then this is actually useful. But system E is actually pointless to have, because you won't be able to kind of fully or like trustworthily delegate to this system. So that's kind of the point where we from which we start in this paper. And then like we were thinking, so how can we actually evaluate score predictability? Well, to evaluate predictability, what you have to do is having something that predicts the performance of the system. So you have to have some score predictors. And this could be many things, right? It could be the AI model itself. So you can either have the AI model output some confidence associated to a specific, let's say, decision that the AI model makes. Or you can have, in the case of language models, the AI model verbalizing, let's say, post hoc, post inference, verbalizing the confidence. You can have a separate judge model where you have another AI model which kind of evaluates the output that the first model gave and tries to assign kind of a performance score, sorry, a confidence score. But you can also have something like an anticipative score predictor. That's what we call it, whereby the score predictor doesn't look at the output of the main model, but simply tries to predict the performance of the main model even before this main model has produced an output, and we call this assessor in our team. So the whole point is that I was saying before that we don't really, well, I mean, we like the average performance on a set of kind of scenarios is not super informative of the usefulness of a model. But at the same time, if you only care about performance of the score predictor, that's not really kind of informative too. So you can consider the following simple example, right? So you assume you have system one, which always fails, and you have a score predictor. Okay, I think someone else is clicking on my slides in some weird way. I have no idea how to disable this. All right, and right. So yeah, all right. So assume that you have system one that always fails, and you have a score predictor, let's say P1, which is able to actually understand this and always predicts failure. So if you only look at the performance of this score predictor, let's say you compute the R2 score or so any kind of performance for a binary classifier, then this predictor will achieve a perfect score. But this is really not informative of what you care about in practice, because this system is still pointless, it's still useless in practice, right? In the real world, even though you are able to detect that the model, you are able to always detect that the model system one will be failing, but still this means that you can't really use it in the real world. Instead, if you have system two, which succeeds, let's say 65% of the times, and you have a score predictor, which is actually able to identify the failures 90% of the times, this seems to be quite useful in a way, right? Seems to be relatively interesting to have such a system. But if you only look at the performance, or let's say the accuracy of the score predictor, P2, then this will be lower than what a P1 achieved. So the point is, what you really care about depends on the underlying accuracy and the score predictor quality. So it's kind of a combination of the accuracy of the main system and the quality of the score predictor. So the point is, what you want to do is considering the AI system and the score predictor pairs as subjects. So you have to consider these pairs of these two kind of entities as subjects if you want to kind of understand how useful they are as a combination. And that's what we try to do, or like that's what we try and formalize in this PredictaBoard paper. And I guess in this paper, what we do is consider a pair of LLMs and score predictors. In particular, what we test in practice are assessors, so this kind of anticipative predictors, but this is just because, we were playing with this setting before, so we just tested this PredictaBoard framework on that. So we are considering LLMs as the main model in this scenario, and assuming, basically considering simple tasks where the model or the LLM is either correct or failing. So for instance, you have this task which comes from the big bench kind of benchmark, where the LLM has to describe or like to guess the name of a movie starting from a set of emojis. So once you have system A, let's say system A will produce a set of outputs, some of which are correct, some of which are wrong, right? And then you may have an assessor or a score predictor more broadly in general that is kind of predicting a confidence on how, like whether these outputs from the system A are correct or incorrect. And you can do the same for another system paired with another assessor. And basically, once you have this kind of matrix, right, you will need to somehow combine the true score, or like the score of the main system, with the predicted score of the assessor or the score predictor more broadly. And that's what we try to do in this work. So just a quick aside, I was telling you that in this paper we use this concept of assessors to as score predictors, and these are somehow small models which are trained to anticipate performance of the main system on a kind of instance basis, right? On an instance by instance. And the way we do this is basically starting from features of the input. So you have, for instance, in this case, some emojis, but you may have any piece of text in the case of language models, and you can extract some numerical features out of it in any possible way you'd like. Then what you want to do is basically take these input features and train a machine learning system to predict the performance of the main system. Let's say, for instance, of an LLM by Mistral in this kind of diagram, starting from the features of the input. So basically, what you do is you do a kind of a train test split of test instances, where test instances is referred to the instances which you use to test the main language model. And then you will of course evaluate the assessor's performance on kind of a holdout set, which you didn't use before to train the score predictor itself. So what's the point of this kind of assessor formalism, where we don't even use the output of the main model to predict if it's correct or wrong? Well, there are kind of two motivations for this. One is that in some cases, if you use a score predictor which looks at the output of the main model, then potentially if this score predictor is powerful enough, and if it is, let's say, for instance, another language model, then maybe this will just rely on knowledge of the ground truth of this answer to basically assign a confidence score. And this is really not what you want to do, or because in a way, I mean, this is not what you want to do in some cases, at least, because in a way this doesn't generalize. So if you find that your assessor or like your score predictor, which relies on the output of the main model, has a very high performance on a kind of simple cases, then this very high performance may just be due basically to memorization of the ground truth, and it doesn't extrapolate to cases where, let's say, for instance, no one really knows what the right answer is. At the same time, if the score predictor model, in this case, what we call the assessor, doesn't depend on the output of the main model, this basically protects it from model manipulation. So this is kind of beneficial for control scenarios. So in a way, like you may imagine in some kind of scenario where the main LLM is producing kind of output which fools the assessor or like the score predictor system. So in a way that the score predictor system, which in a way is acting as a monitor, is is going to be fooled and kind of predict that this output is correct. And this clearly cannot happen if the assessor is only relying on the features of the input. Okay, this is basically just an aside because I think in the paper, I guess if you read the paper originally, we framed most of the paper around this assessor from kind of formalism, which I think is mostly a historical reason. We were working on this and we built this PredictaBoard to test these tools we were developing. But to be honest, like the formalism of PredictaBoard works with any other score predictor, be it kind of the LLM self-confidence or a judge model or any other kinds of score predictor. Right, so going forward, if there are no questions at this point, I mentioned before that once you have a system and a score predictor, you will get this matrix, which is basically let's say a two-dimensional matrix where for each benchmark element you have what the system actually achieved. So if the system was correct or wrong on each of these elements, and then the score that the score predictor assigned to the score predictor assigned to the model, the main model being correct on this specific instance. So how do we actually extract any meaningful metric out of this to the two-dimensional matrix? So as I was kind of arguing or like giving an example about before, if you consider some common metrics such as the mean squared error, the area under the ROC, or S-squares, for the predicted model, so for the score predictor's performance, basically these are ignoring how well the main model does, right? So again, like recall it from before, if you have a model, system A, which always fails, right? And the assessor or score predictor is able to perfectly kind of guess this will give a very high score for the score predictor, but this is really not representative of potential for real world use of this pair of systems. So what we kind of use is this idea of an accuracy rejection curve, which is not, I mean, we didn't really introduce this, but someone else did in 2010 actually. It's a fairly like relatively old idea, and it's actually a very simple idea to. And what's the point here? So the point is that you build this two-dimensional graph where on the x-axis basically what you do is you assuming that your score predictor outputs a number between 0 and 1, so it is some form of probabilistic predictor, then you can set a threshold, right? And reject all of the benchmark elements for which the score prediction is below that threshold, all right? So let's say that you set the threshold to 0.5 or like let's say 0.65, just because the threshold number is not really important. It doesn't need to be anything specific or not ordinary. So let's say that you set 0.65 as a threshold. So in this case, specific example right here, you will reject this to the element number 4 and element number 5, right? And that means that if if we assume that there are only 6 elements, we would have a rejection rate of 33%, and that's somewhere about here. So what you would do now is then look at the non-rejected instances or non-rejected elements of the benchmark, which are the first 3 and the last one. So in this case, you would have 4, and the model is correct on 3 out of 4. So you would have an accuracy on the non-rejected instances of 75%. So basically what this means is that for a rejection rate of 33%, then the y-axis represents the accuracy of the non-rejected instances of the benchmark. And in this case, it's 75%. So if we actually did this with this simple matrix, it would be somewhere around here. Let's say around here. Right. So basically, what you could do then is do a sweep of the values of the threshold from like 0 to 1, and build this kind of graph, build this plot. which is in a way, the idea is similar to how you build a receiving operating characteristic curve. In the same way there you have to vary the threshold of the binary classifier. But the main difference here is that there are kind of two systems, so that you compute the accuracy on the non-rejected elements. So I see there is a hand raised.
Yeah, I was trying to, because I mean it seemed like part of the point of introducing these plots is that they're like, helpful for like a model developer or person who's doing control stuff and wanting to see like the performance on various things, right? So I mean just basic reasoning, and sorry if you sorry about the plot, things moving without you going for it, but yeah, so in like what would be, I was trying to imagine what the basic case would be where maybe you have like, you understand that like the model was like having like a fixed threshold. I'm sorry, not a fixed threshold. Like it was only the fixed like error rate, So like the model was only ever, some distance from in its confidence when it was, let's say it was evaluating itself. And it was only ever, maybe like 0.01 away from the true value, right? So in that case, like you would see in this plot, like there'd be like this kind of like a line that in the upper left corner, like it like would go up like at a sort of steady rate as the rejection rate went to 1, and then it would just sort of plateau and it would just hug the top, right?
Mhm.
Is that right? I'm just trying to imagine what are the kind of the simple cases of this before thinking about the complex ones.
Um, Yeah, so I guess the simple cases would be, like, even simpler than that, would be cases where, let's say, the score predictor or the confidence of the model is constant, right?
Mhm,
Or is randomly distributed.
mhm,
If it is constantly of random or randomly well, if it is randomly distributed, then basically this line would be flat, right? And it
mhm.
would be always the accuracy, assuming the data set is large enough, of course, right? It would be kind of flat at the accuracy level of the model on the main benchmark. If it is kind of a single fixed value, so if there is a single value, so basically this doesn't really make sense because we can't really vary the rejection rate. Um, if it is something like um, yeah, I'm thinking about your example. If it is something like the model being kind of always confident, or like, let's say assuming that the model always gives confidence 0.9 when it is correct and confidence 0.1 when it is not correct. This would be kind of a jump function from yeah, from here to the 100% location, right? And why is that? So the reason for that is that so the x-axis here is the rejection rate. So it's not the threshold that you use. So basically this means that this curve is kind of invariant to monotonic transformations of the values that the score predicts in the same way as the area under the receiving operating characteristic curve, if that makes sense. Um,
Yeah. And like in the way that that you plot this curve is that you sort of you take the confidence or the assessor's
yeah,
level and you kind of sort. It's as if you
yeah,
sort the
yeah,
the
yeah, basically.
scores
Yeah.
by that column,
Yeah.
say from most to least, and then
Yes.
sort of you're always taking like the top n or something
Yeah.
like that, right?
Yeah.
So,
Correct.
and that's how you get this kind of curve.
Yes.
So
Yeah, that's
if
correct.
you were right, oh, like towards the end, as you get to your top, only like your top 3 or whatever, like you expect those to be the ones where it starts to
Mhm.
hug the top because it's
Mhm.
the
Mhm.
top one, the top 3 we expect are going to probably be the ones where I'm sorry, the top 3 of like 100
Yeah.
most
Yeah.
confident, we expect those to be the ones that are always accurate because
Yeah, exactly. That's the motivation. And yeah,
yeah,
yeah.
yeah.
And I will show you some like real curves later on. And
Cool.
there is an issue. The issue is that, as you increase the rejection rate, you have fewer and fewer samples. So this becomes noisier closer to this part. But I will show you later, maybe Yeah, and I guess the whole point, the whole motivation is that if you were just to, let's say, consider this toy example with the system A and system B, which is this dashed line, and I just deleted the kind of the label here. But if you were only to look at the overall accuracy in this toy case, system A seems to be much better, right? But if you are instead doing this kind of, if you're relying on another, on the model's confidence or something else, and you just use the model in the top like 20% of cases, that you can see that you can actually get 100% accuracy with those on those non-rejected cases for system B. But system A instead is much worse. So the whole point is that at different like kind of error tolerances, you may prefer one model versus another. Right. So maybe I can go ahead with this, and because I still have a couple of slides on this kind of graph. So I guess the point is, right, from the perspective of the score predictor, the accuracy of the primary model is just basically the precision of the score predictor. So it's how many of what the score predictor said are going to be correct are actually correct. So it's true positive over true positive plus false positives. On the other hand, the rejection rate is a bit more complicated. So there's not really any kind of clear connection between these. I mean, there is some connection with this and the precision and recall, which are usually used in this scenario. But it is a bit more convoluted. It's not like a straightforward connection. So, okay, so I've talked about this curve quite a lot, but this is still a curve, right? So it's not really a number. How do we actually get a number from this such that you can actually choose what kind of system or system score predictor pairs are best for your use case? So that what we kind of talk about in this paper, what we propose is to do the following. So assume you have an error tolerance. Okay, so assume that in your application you have an error tolerance of 20%. Okay, so you can accept that when your system is actually used, so when the tasks that the system is assigned are not rejected by the monitor or the score predictor, then you can tolerate 20% of errors, which is quite a lot, but just for the sake of example. So what we do is basically looking at this curve, you just take plot an horizontal straight line, right? And look at where this intersects the accuracy rejection curve for one of the two systems, or like for one system that you are considering, and basically computing the maximum coverage, so the minimum rejection rate, or like one minus the minimum of the rejection rate. And we call this the predictably valid region for a given kind of error tolerance level. So in this case, let's say if you had a 20% error tolerance, then we call this the predictably valid region at the level 0.8 of precision that you want. Basically, the point is that if you have these two systems, which are again similar to what I was showing before, because they cross in this point, let's say if you have a 20% error tolerance, then for system A, you can actually identify that with the use of using the kind of the score predictor, which comes together with system A, you can identify 80% of your use cases where you are sure that the error tolerance will be lower than 20%, right? While on the other hand, if you consider system B, then this will basically be 60%, which is a lower value, right? So it is worse. So basically this predictably valid region is just representing the maximum coverage across different systems at a fixed precision for the score predictor, right? So again, you want to have precision which is as high at least as high as 80%, or error tolerance which is at least as low as 20%, and you look at what system allows you to have the largest coverage or the lowest no rejection rate for this. So this is a bit convoluted, I know. So I hope it's not too complicated. And of course, and this gives you kind of a numerical value, right? In this case, it's 0.6, in this other case, it's 0.8 for this kind of error tolerance and these two toy systems in this example. You can also get something else, such as, computing the area under this curve. And that's kind of an integral, if you want, like an integral average of these numbers over all possible rejection rates. Right, so this is basically the whole setup that we introduced, which is, kind of simple. I think the main methodological kind of hurdle is interpreting these curves correctly, which it may take a while to actually sink in. So the rest of these, in the rest of the slides, I just wanted to present some experimental results which we obtained. So I'm gonna go and do that unless there are like any urgent questions on like interpreting this curve. Right. Okay. I'll go on then. Just take a sip of water. Okay, so we did this. We introduced this framework, but then we also conducted some experiments with a bunch of language models. So what we did is basically take a bunch of language models from Hugging Face, and there is actually an open source. Now I forgot the name actually, but we got results of all of these language models on MMLU Pro and Big Bench Hard from kind of a benchmark or leaderboard on Hugging Face. I can't remember the name anymore, but it's one of the most famous. So we didn't really run any of these models. And then on top of the open source ones, we also got results for some of the GPT family models for the MMLU Pro dataset. So we have something like 41 LLMs. We have their results on these two benchmarks. One of which we used as a training set, or at least we use as a Dean distribution benchmark. So we take a subset of it to train our assessors, where the assessors we use are basically just very simple machine learning or like statistics, depending on your preference. Models such as logistic regression using some sentence embeddings of the text prompt of the MMLU Pro or Big Bench Hard in this case. So what we do is basically just take the prompt, put it through an embedding model such as the OpenAI embeddings or very simple ones such as the ngrams, and then train one of these classifiers to predict each of these models' performance on the train set of MMLU Pro based on the features, on the embeddings. And this is what we get. So I'm showing here some of these accuracy rejection curves. And this is for one fixed LLM, and that's the LLM which had the highest accuracy in our dataset. And the different curves basically represent different assessors with different kind of text features, different predictive methods. So it's kind of interesting, I think. It's kind of a neat graph in a way, because you see that clearly when there is no rejection, the accuracy is the same, the assessor is not really playing any role. So the accuracy is about 76% or like 75 something in this case. And then with different models, different assessors have a more or less better, are more or less able to sort the models, sort the output, sort the elements of the benchmark based on whether it is more or less likely than the GPT-4 in this case is answering them correctly or not. So it's kind of interesting that the best assessor in this case are those using the OpenAI embeddings, which is not surprising because they are more powerful in a way than other simpler embeddings. And as I was saying before, these curves get more and more noisy when it comes to higher rejection rates, clearly because there are fewer elements in your non-rejected sample. This is another example which is just interesting because it's actually an example of a small kind of these two curves actually intersect. And this is actually fairly rare, to be honest, and with the models and assessors we use. And that's actually, I think, because all of the models we use are poorly predictable with with the assessors we used. So this graph is basically showing for different thresholds. So this is for 20% error tolerance, 10% and 5% error tolerance. And this is showing basically the coverage, the maximum coverage that you can get. So what this, let's say 0.162 means is that with this LLM and this assessor, what you get is that you can actually identify a 16% of the test set where the model has an accuracy above 90%. That's what this number means. And you cannot really identify a larger subset than 16%, right? So that's the largest subset of the test set where the model has an accuracy of at least 90%, which you can identify with your assessor. As you can see, this is basically fairly low for high value. So, like it's not like even though this GPT-4o model has something like 75% accuracy, right? Or no, actually even more, because otherwise this would be incorrect. So it's like 80-something% accuracy. Then you can't really go above 20% of the as a subset size for your test set, which you can identify with a kind of a guarantee that the performance is above 90%, which basically means that it is very hard to sort how well elements of the benchmark based on how well the model itself can answer them correctly or not. Okay, and this is in distribution, right? So this is already fairly bad in distribution. If you go to out of distribution, this is much worse. So yeah, the numbers are lower. I'll just move on here because it's not, they're just much lower. This is something else, which is kind of a neat investigation, I think. And maybe I think, Kim, for the sake of time, I may kind of stop here and skip this slide for now because, otherwise we won't have any time for discussion. And this is a bit more in-depth. So kind of a quick recap and conclusions and takeaway messages in a way. So the whole point of this PredictaBoard framework is to jointly score an LLM or an AI systems more broadly performance and the predictability of its performance. Okay, so and the metric we used mainly is this predictably valid region, which basically consists of fixing an error tolerance and counting how many samples the LLM score predictor pair are able to tackle with an error below that tolerance. And of course, like we release kind of some baseline assessors and results for all of these LLMs. So the whole idea is that by introducing this kind of predictability prediction framework, then we can try and develop more predictable LLMs, so language models which are going to succeed or fail on cases that we can actually identify. Yeah, and of course you can extend this to other notions of validity beyond correctness. You can potentially try and predict when the output of a model is kind of toxic or other kinds of validity notions that you want to use. And you can also try and extend this to non-binary scores, while what I presented here is mostly for the binary case. So yeah, thank you very much. These are a bunch of links. And yeah, I have to thank all of my co-authors on this paper. It was kind of a joint effort. But thank you very much for listening. I'm happy to take any questions.